Alright, so today we're going to be going over MacBook Pro with nothing on the screen, and we're going to make a couple of quick measurements to see what's going on in the circuit. Before we do that, I want to see if I can find myself a sample diagram that's worthwhile here. One of the funny things here with this whole argument, and I think a lot of people are missing out on, when they say, oh, that's special, that's a secret, that's this or that or the other. What I think they're missing out on is that the circuit is almost the exact same as what the actual manufacturer includes in their own diagram. So if I were to just go over here to this part of the screen, and I were to zoom in over here, most of the chipsets that I'm replacing are teaching you, what the things do. They come with these little simplified schematics, and the whole idea here is that it's pretty much telling you how to recreate the exact same circuit. And it's usually almost the exact same thing as what the manufacturer will use. So if we were to look over here at this little diagram, this is a backlight boost circuit, and you have the beginning, which is going to be 5.5 to 22 volts. In the case of our machine, 12 volts. And at the ends of it, you're going to have something around 27 volts. Now, you're going to have the enable pin has to get 3.3 volts. The PWM pin is going to have to get a little wave for the brightness to work. So if we were to attach this, the first thing that I like to do when it comes to any of these situations is measure the voltage on output. See, knowing what the voltage on output is going to tell me a couple of things. So for example, 0 volts means most likely backlight fuse is blown, or that it just doesn't see a screen. Let's say 27 volts would say bad screen. 18 volts would say something is going on most likely with the boost IC. The boost IC is probably bad. And something below, like at 50 or 51 volts, is going to say that there's a break in the line. So let's say the screen cable could be bad, or the LCD connector could have a burned pin. Now, something along the lines of, let's say, 0.5 volts or 1 volt or 2 volts is going to also mean a break in the line, but that's going to be a break in the line earlier on. See, the reason I would get a higher voltage if there's a break in the line at the end is that if the boost circuit is working, let's say the boost circuit is actually working, but it doesn't see a load. Let's say it's trying to make 27 volts while powering a screen. If there's no screen at the end, or the backlight is part of the screen is broken off, then it's going to try to create 27 volts for a load, but if that load doesn't exist, then it's going to deliver more voltage than it should. So think of it like arm wrestling. Like, let's say you're arm wrestling and you're trying to beat the other person, right? And using as much force as you can. And the other person just decides to go limp for a second. Your arm is going to smash its way into the table because you were expecting the resistance of that other person who's trying to beat you in the arm wrestling match. If that resistance goes away, now you're putting all that pressure into nothing. The same is true here. So let's just check out the different voltages we get. Now remember, if it doesn't detect the screen, that's different than the backlight part being burned out. So let's say it detects the screen, it sees the image and all that, but the one line that's required for backlight is broken. That's when you'll see the really high voltage. However, if you see no voltage because it doesn't detect the screen, that means that there's something wrong with the graphics, that there's something wrong with the LCD itself, or there's something wrong with the DDC circuit, which is all totally separate. So when I check backlight output here on the multimeter, I'm never going to learn how to record YouTube video, man. This is bullshit. It's bullshit. It's like, regardless of what camera angle I use, something doesn't fucking work, or fuck this. We're going to move this desk. Yeah, motherfucker. Here we go. Use those muscles. All right, so now we're in view. So let's check output here and see what we get. So in output of backlight, we get 1.5 volts. Now keep in mind, this is a circuit that's supposed to take 12 volts and turn it to 27. So 1.5 doesn't make sense. Like 0 would mean blown fuse, or it doesn't detect the screen. 12 volts would mean no break in the line, but there's boosting. But again, that like 1.5, something is partially broken in the line. There's something that's intermittent there. And usually that's going to be somewhere back here. Let's see if I can show you. So usually that's going to be somewhere by, let's make sure, see, are we connected here? Can you see what's on my screen? Hope you can. I forgot to turn on the second monitor that allows me to see what you see. Let's double check here. There we go. Bam. So this, where VBAT attaches to the inductor, sometimes that can be bad. So we could trace our way back through the entire circuit. Now, I do know, based on a little birdie telling me, that the voltage from from here, that's the input to the coil, also goes to enable, right? So if I wanted to do a quick check, what I could do is I could measure the voltage right at the resistors that lead to enable and see what I get there. 1.7. So same shit. So the entire input to this circuit is getting me virtually nothing. Now if I were to check at the backlight fuse, bam, 12.5. Bam, 12.5. So here's the way this works. So there's a backlight fuse. Wrong view. There's a fuse that goes between the 12-volt rail in here, and then there's a transistor over here that then allows power to flow through to here, it allows it to flow through to here, and everything else. So now what I'm thinking, if there's power at the fuse, okay, we're going to have drawing time with Lewis. So we're going to put a fuse, and that's going to go to a that's going to go to a transistor. Here we go. Image. Bam. Ahem. Yeah. Do this. There we go. Alright, so the way this works is this is a transistor over here. So this is going to allow power to flow to the backlight circuit. So this is going to be the source, this is going to be the drain, which is the output, and this is going to be the gate. So the way a transistor works is the power is going to flow from the source to the drain depending on what's on the gate. Now the whole idea here is you don't always want the light to be on, so the CPU over here is going to tell the transistor when to allow power to flow from the fuse to the entire backlight circuit. So what we have over here is a case where the output is 1.5 volts. Over here, so this we measured 1.5 volts. Now over here we measured 1.5 volts. Over here we measured 1.5 volts. Over here we measured 12. Over here we measured 12. So the issue is either that the transistor is not opening, right? The transistor is not opening the way it's supposed to, or there's a break in the line. So for example, right at this transistor there's a break where it goes from here to here. So our two issues could be either the transistor is fucked, like this. Hopefully I have Control Z because I did a lot of good drawing there. Or there's a break in the line like this. Make sense? So what I'm going to do now is I'm going to flip the board around. I'm going to turn the microscope camera on, and then we're going to see where the break is exactly. Okay, so as you can see here, this is a standard customer MacBook, very clean, very well taken care of, you know. Very, very clean, you know. Just standard stuff. Hey, Lewis, why do you wear gloves in your videos? Hey, Lewis, why do you wear gloves in your videos? Hey, why do you wear gloves? Hey, do you have OCD, man? Why do you wear gloves? Why do you have to wear gloves to touch a computer? Hey, I don't get it. Why do you always wearing gloves in all these videos? Yeah, you like that? You like that? You want to touch that? If I gave you $1 million to lick that clock chip, would you accept that $1 million challenge? $1 million to lick this motherboard. The right to repair bill would be passed if I licked this motherboard. You know what? I'd rather just throw shit away and go to the Genius Bar. Anyway, so fuck that. So, okay, let's measure. Let's measure around. Let's stop fucking around. Alright, get the... Motherfuck, I can't get camera angles right to save my life. Okay, now I do this. Oh, I have to do this now. So you can see shit. Oh man, I suck at filming. Alright, so let's check out what we get at the output of the transistor. So the transistor's output is 1.8. Transistor's input, we got 12 on M. Oh, here we go. Okay, so this is... Alright, so let's reconvene here. Let's get it. Alright, so this is a bit of a better version, I think, of what's going on. So the way that this works is you have 12 volts going through a fuse. From the fuse, that power goes to a transistor. And from the transistor, that power then goes to the circuit. Now, the whole idea is the fuse acts as protection. However, the transistor is going to be what lets the power flow through. Now, the whole idea here with the transistor is that the voltage on the source has to be higher than the voltage on the gate in order for this to actually open. So this is a long story short with transistors. The way this transistor works is the voltage in the gate's got to be lower than the source, or else this will not let power through. So how are we going to get the voltage on the gate to be lower than the voltage on the source? Well, here we have a voltage divider. So we have this voltage divider that's going to take the voltage from the source and place it on the gate, and then this second resistor in the voltage divider is going to take the voltage from the gate and bring it to ground. But only if the CPU says that it should go to ground. So the CPU is going to determine whether this transistor opens. Now, the problem that you saw when I was measuring is that on the source I had 12 volts, and on the gate I had 12 volts. So if the source is 12 volts and the gate is 12 volts, this being a P-channel MOSFET is not going to want to open. So there's a couple of things that could be going on here. The MOSFET could have an internal short between the source and the gate so that it's never going to open. The MOSFET could be broken. Or the issue could be that this capacitor over here is shorted, right? So this 147 kilo ohm resistor is going to take the voltage and bring it to ground. It's going to lower this to about 5 or 6 volts. However, if this capacitor over here that's sitting between the fuse and the source and the gate is shorted, it's broken, then this resistor over here, instead of it being 301 kilo ohms, it's going to be the sum of the resistance of the now shorted capacitor and this. So there are a number of different things that could be going on here. Or it could simply be that the CPU is not allowing the voltage divider, the CPU is not telling it to open. So the CPU is not opening this, meaning that the voltage divider is not going to work. So the way a voltage divider is going to work, the voltage divider is going to lower your power, or lower your voltage, but it's going to lower your voltage by sending some of it to ground. So you have a resistor between 12 volts and where you want 5 volts, that's this one over here. And then you have a resistor between where you want 5 volts to be in ground. So some of your power is going to go here, some is going to go to ground. So if this doesn't have a path to ground because this other transistor is not opening, then you're kind of fucked. So let's take a look and try to figure out which of these things is the actual issue. So I'm going to measure the 301 kilo ohm resistor, and let's see what I get for that. So that's supposed to be 301 kilo ohms according to Microsoft Paint, and I get 4 kilo ohms. Now, again, let's just use some logical thinking here. Let's just use some logical thinking. So if my resistance between this point over here, if my resistance between, let's get a brush and make it a nice color. So if my resistance between, where'd the mouse go? Hello, mouse. There you go. If my resistance between here and here is 3 kilo ohms instead of 301 kilo ohms, what are the potential issues? The first one is that my capacitor has shorted. So if my capacitor breaks, instead of it being 2 plates like this, it's going to be 2 plates like this that are touching, and then this becomes lower. Now, it could also be that my resistor has been destroyed. If my resistor gets destroyed, then it could be that my resistance is much lower. But that's very unlikely. When a capacitor fails, it fails by becoming a lower resistance. When a resistor fails, it usually fails becoming a higher resistance. So again, this is a ceramic capacitor here. So any one of these capacitors where you can see it looks kind of orangey, like this, that's on these boards, it's usually a ceramic capacitor. So if this has failed, it becomes a short circuit, and it becomes low resistance. Whereas if this fails, I hate not being able to see where this damn cursor is, then this usually becomes a higher resistance. So I'm not really inclined to blame the resistor. Now, it could also be a failure of the transistor itself. If the transistor has failed, source shorts the gate, and bam. So I could remove the transistor, or I could remove the capacitor to try to see which is at fault here. So I'm going to remove the speaker, I'm going to turn on the air filter because I'm pretty sure that as soon as I put any heat on this board, I'm going to smell whatever this person has been eating for dinner for the past 5 years and dumping into their fucking computer. And we'll see which one it is. So place your bets. Do you think it's the capacitor that's bad or the transistor? I'm placing my bet on the capacitor because it's very, very unlikely that a component as large as that transistor has failed. But I can always be wrong. So, I'm going to go over here. I'm going to turn the air filter on. Even with the air filter on, I'm not going to inhale flux fumes, but I'm pretty sure I'm going to smell whatever this person ate for dinner. Oh, look at this. What is this, fucking larvae? Yeah, let me get that in focus. What is this? Is a moth going to pop out of that? Come on, people. Alright, so the capacitor has been removed. So at this point, I'm going to measure for resistance. And see if anything has changed here. I still have 3.8 kiloohms. So at this point, I'm going to remove the transistor. My bet was wrong. Fuck. Can't win them all. Okay. Hey, sometimes you win, sometimes you lose. So let's see what I get now. 300 kiloohms. Okay. So let's go over this on the screen again. At least there's one brain in the damn screen, because I surely don't have one. So what was going on here, and God, I can't. Here we go. I can see it now. So what was going on here is I removed the capacitor, and when I removed the capacitor, this resistor was still measuring 3 kiloohms. Now remember, just because I'm measuring 3 kiloohms here does not mean the resistor itself is 3 kiloohms. I'm measuring the resistance of everything between this point and this point. So there's a capacitor, a resistor, and a transistor connected there. So I removed the capacitor just in case that was what was doing it, and it wasn't. But when I removed the resistor, the resistance that I measured between this point and this point went up from 3 kiloohms to 301 kiloohms, which means that this transistor was shorted. It had a short between its source and its gate, and that's why I was getting 12 volts on the gate, even though this entire circuit was working. So now we're going to replace the transistor and see what's going on there. What do you think of my schematic? What do you think of my schematic? You know what, I should at least write my influences here. Inspired by I'm just kind of curious. Can I actually draw that little stick figure guy? No, I can't. I suck. I shouldn't. It's garbage. Yeah, watching those gave me the inspiration to not just stop doing videos. So thank you, grade. I thought that paint would have been too hard for me to figure out and comprehend. But you have shown me that it's not. I must have watched his video with the hacking thing like 30 times over. Not the entire video, but just the point where the little stick figure gets asked, "What's your real name?" Yeah, okay, just what's your real name before we send you the SIM card? Beautiful. I mean, that shit is hilarious. I mean, it's just that stuff is universally hilarious. Beautiful. And then the T-Mobile guy hangs up on him. Okay. Oh well. Okay. Now remember, the bottom 4 legs are all shorted together. They're actually shorted together on the board purposely. No, fuck. That's fucking fine. All right. Ta-da! And that's that. I think I'm getting better at Microsoft Paint. What do you guys think? I think I'm starting to make some progress here with Microsoft Paint. So that's that. Hopefully you learned something.